Today we're going to learn about power series, specifically geometric power series. We're going to find the interval of convergence of a geometric power series and also differentiate and integrate them. What's the difference between a power series and a regular series? Here are some examples. What do you notice? Power series always has some sort of an x in it, a variable. Power series allow us to write functions of x as a series rather than in their function form. And why would that be important? Well, 3 Blue, 1 Brown has an incredible video that talks about Taylor series and being able to represent a function of x as a series, because a series is in polynomial form, and polynomials are much easier to deal with than rational functions, root functions, or other types of functions of x. So let's begin by taking a look at this power series. A series with variable terms like 1 plus x squared plus x cubed plus ... plus x to the n plus ... is called a power series. Note that this series is a geometric power series. If it's geometric, let's find its common ratio. It looks like that would be x. To find the sum of a convergent geometric series, we need its first term and we need its common ratio. And then its sum is a over 1 minus r. Oh my goodness, 1 over 1 minus x is the function form of this geometric power series. Here's our summation form. Remember, to know which number you start at, you just plug it in to check. When we plug in 0, we get 1, our first term. For this geometric power series to converge, we need the common ratio, or the absolute value of the common ratio, to be less than 1. This interval is a compound inequality where x is less than 1 and greater than negative 1. Therefore, the interval of convergence is negative 1 to 1. If x is a value on this interval, then this geometric power series will converge. If x is not on this interval, then this geometric power series will diverge. You have, as a reminder, geometric series can look like this or this. The sum of a convergent geometric series is this, which is extremely important for when we want to write a function of x as a geometric power series, or when we want to write a geometric power series as a function of x. And remember that for a geometric series to converge, the absolute value of the common ratio must be less than 1. Therefore, even though your common ratio now has x's in it, you can still solve this inequality and find your interval of convergence. For the following examples, we're going to find a power series for each of the functions, show 4 terms and the general term, also give the series using sigma notation, and give the interval of convergence. For number 1, our function of x actually looks a lot like the function of x that we got from the very first geometric power series. In fact, the only difference is this minus sign. So first, can we do some algebraic manipulation to make this function look like our beautiful sum formula? Yeah, I could rewrite this as 1 minus negative x. All right, now a is equal to 1, and our common ratio is negative x. So as a sum, a times r to the n. Now, this may look like the simplest way of writing this summation, but in fact, if you have a negative 1 to the power of n, we want to take that out and write it separately. It's just going to make it a lot easier for us to see if we have an alternating series or not, which this one is an alternating series. And that is super helpful for later on. To find the first 4 terms, let's just plug in 0, 1, 2, 3. This is a series. They asked for the first 4 terms and the general term. Since we already wrote it in summation notation, we know our general term. But it's important that our series notation is always on point. What do I mean by that? This is a series, so I need to have a plus ... And then I'm going to show the general term. So we're going to put another plus, but it's a series, so it doesn't stop there. So we write another plus ... And you can see that we've shown the first 4 terms and the general term. Our last step is to find the interval of convergence. For your interval of convergence, the absolute value of r must be less than 1. That means the absolute value of negative x must be less than 1, which gives us a compound inequality of -1 to 1 with negative x in between. Once you divide all 3 parts by -1, we flip those inequality symbols and we get the same interval as the first power series. That interval of convergence is -1 to 1. Let's try number 2. My first term would be 3, and it looks like that common ratio, since you already have a subtraction, that common ratio would be 2x. That would make our summation notation It could also be written with the 2 to the end separate. Plug in 0, 1, 2, 3 for your first 4 terms. Now I'm going to include the general term, but I can't just say plus the general term because there are many terms in between, so I must write plus ... plus the general term, which is just what we wrote for the summation notation. And this is an infinite series, so I need to conclude that with plus ... Otherwise, your notation is not completely correct. For our interval of convergence, the absolute value of our common ratio must be less than 1. I can take the 2 out of the absolute value because it's already positive and divide both sides of the inequality by 2. Now I'll split to make it a compound inequality. And our interval of convergence is -1/2 to 1/2. As long as x is a number between -1/2 and 1/2, then this geometric power series will converge. Now, number 3 is a little annoying because it has one term in the denominator, and we're supposed to have a 1 minus in order to know that this would be the common ratio. But I don't have that, so I'm going to have to do some algebraic manipulation in order to make that happen. The first thing I'm going to do is add and subtract a 1 in the denominator. Alright, I still don't have a 1 minus, so I'm going to factor out a negative from the 3x and the -1. Now I know that, well, I always knew my first term was 1, but now I know the common ratio is -3x plus 1. As usual, it's better if x doesn't have a coefficient, so I'm going to factor out a -3 before writing it in the summation form. Apply the n to the -3. We factored out the -3 so that the coefficient of our x is 1. That is the most simplified version of the nth term. Also could be written by taking out that -1, the alternator, and we could write it like this, or even with the 3 to the n separated. Let's find our first 4 terms. And there is our series. Oh wait, I'm missing something. Plus ... This is an infinite series. Do not forget to show that. And now to find the interval of convergence. The absolute value of r must be less than 1. I can take the absolute value of -3 separately since it's a product, so that would be +3, absolute value x minus 1/3. Then I'll divide by 3 on both sides. Now I can rewrite as a compound inequality and add 1/3 in all 3 sections. That makes our interval of convergence 0 to 2/3. Using the power series from example 1, make a new power series for f of x squared. Here's our series from example 1. Instead of f of x, though, we want to find f of x squared. So every time you see an x in the original power series, you'll replace it with an x squared. And then I'll write it one more time, simplified. For number 5, we're going to use the power series from example 2 to make a new power series for g of root x. So for this one, we're going to take every x and replace it with a root x. Often we write things as powers, so you could rewrite the root as a power of 1/2, and that would also be an equivalent power series. Use the power series for f of x equals 1 over 1 minus x on the previous page to write a power series for f prime of x. This was the very first example we did before we even did example 1. To derive a power series, you just take the derivative of each term. That's the beauty of a power series. It's much easier to derive because it's in polynomial form. That could also be written without that 0. If j of x is equal to the following series, then find j prime of x. Go ahead and derive each term. Remember this expansion, that n factorial is equal to n times n minus 1 factorial, or you could keep expanding times n minus 2 times n minus 3, and you can keep going, but whenever you want to stop, you just put the factorial, and that says, hey, it keeps going. I just expanded 2 terms so that we could reduce the n over n. N over n, so we've got several things we can reduce here to give a cleaner version of j prime of x. What did I do wrong with my notation in that first step? I don't have a plus dot dot dot. Even after the general term, you have to have a plus dot dot dot. There is the simplified version of our derivative series. Since 1 over 1 plus t is a function represented by the power series, we figured this out in example 1, integrating both sides from 0 to x will give us our integrated power series in terms of x. The integral of 1 over 1 plus t, or u prime over u, would be ln, the absolute value of u, evaluated from 0 to x. And we can integrate each term individually. The integral of 1 is t minus t squared over 2 plus t cubed over 3, negative 1 to the n is a constant, but we will add 1 to the power of t, and that will also be our denominator, evaluated from 0 to x. Show the subtraction. Beautiful. Let's continue to simplify. By integrating 1 over 1 plus t, we have now found the power series for ln absolute value x plus 1. Use the result of example 8 to write a power series for ln x. If I call the function in example 8 h of x, how does that transform in order to get f of x? If you graph this series, as you keep adding on more and more terms, you're getting an approximation of ln x plus 1, not the absolute value side. So this series is equivalent to ln x plus 1. If h of x is ln of x plus 1, how am I going to rewrite that series so that I now have a series that represents just ln of x? What transformation is happening from h of x to f of x? H of x takes f of x and is adding 1 to each of the inputs, which means to get f of x, we need to subtract 1 from each of the inputs in h, and then we will just substitute an x minus 1 every time you see an x in the previous series. Here is our new series for ln x. Here is our series for ln x. Now write a series for g of x, which is x squared times ln x. So g of x just takes each term of f of x and multiplies it by x squared. You could obviously distribute in that x squared here, and the rest of your terms would be the same. And either of those answers would be acceptable.